take in slightly different images?
Okay, so you've got two retinas, right? So if you only had one, if you were a Cyclops, then you would have no three-dimensional visual ability, right?
That seems wrong.
Yeah, that does seem wrong, because if you cover one eye, you can still navigate space, right? So you can still tell, for example, that the table is closer than I am. So retinal disparity is important, don't get me wrong, that your brain actually does take a lot of information from the two different eyes, and it pays attention to the difference between these two vantage points. But that's not the whole story, right? So we're going to start with the retinal disparity, because that's the more obvious thing. But then we will talk about what's going on with one eye. So if you're a pirate and you're dark adapting one eye, can you still run around? Or if you've actually lost one eye, can you still run around and swashbuckle and whatever pirates do? So the first thing we use are called binocular cues, because they require two eyes. So your two eyes get slightly different views of the world. They're about 2.5 inches apart. So the comparisons of these two viewpoints produce depth perception, or what's known as diplopia, or double vision and stereopsis. So you can do the thumb test that we talked about earlier, or the figuring out which is your dominant eye. So if you hold up your hands like this on a point, and you close one eye, then the image shifts. So the thumb test is if you hold up your thumb, and if you cover your thumb with a barrier, then you can still see it from one eye, but not the other, is the idea. No, you line up your thumb with an object, and then you close one eye. That's what the barrier is your eyelid. Then your thumb is going to move. It's going to be lined up with the object in one eye, on one retina, but not with the other one. So that's the idea here. So if you're left eye dominant, and if you line up your finger with the far object in your left eye, then they both hit the same place on your retina. So if you close your right eye, it's not going to move. But if you close your left eye, and your left eye dominant, then the two objects are going to fall on different places on the retina, and you're going to have a difference between those two things. So the way that we calculate distances is based on what's called angular disparity. So this is the disparity between the images in the two eyes. What is the angle of that difference? So all points in the visual space fall on points in the retina. It's just saying the same thing, right? Points in the retina can be mapped according to how far away they are from the fovea. So what is the angular distance from the fovea? For any given point in visual space, the angular disparity equals the difference between the angles and the two retinal locations that the image falls on. So angular disparity in degrees, that's AD, is equal to the angle in the right eye minus the angle in the left eye. For our purposes, it's always going to be right minus left. So for all points of the same depth in space, same depth in focus, the angular disparity is going to equal 0. It's all going to fall on the same point. So these visual points are what's known as the horopter, which sounds like something from Harry Potter, but it's not. It's actually kind of cool. So the angular disparity occurs when points fall off of the horopter, either farther or closer, and there's an ordered relationship between the angular disparity and whether it's closer or farther away. So if you're focusing on the point with the blue line, so that's falling on your foveas, on both of your foveas, you're focusing on that point. Let's say that's at the screen. The horopter is an imaginary line around you that's mostly circular, it's basically circular, where all of the points along that line are the same distance from you, and there's 0 angular disparity between the two eyes. So if you were to take the angle in the right eye for the orange one, 30 degrees, minus the angle in the left eye, 30 degrees, that comes out to be what? 0. So there's 0 difference angular disparity. or zero angular disparity between these two. Same thing for the purple points, the red points, etc., etc. They all subtract out. So they're all corresponding. So the image that's falling on the left retina is exactly the same as the image that's falling on the right retina for all of the points at that distance away from you, at the distance at which you're focusing. But what about things that are closer? So what about our thumb test? Well, it turns out that if you're focusing on the screen up here, your thumb is closer, right? So there is going to be a difference between the angular disparity of your thumb and what's on the horopter. So things that are closer than the horopter fall on non-corresponding points in the retina, yielding crossed disparity, greater than 0 degrees difference.
Does your horopter change depending on where you're focusing?
Yes. Yeah, so the horopter corresponds exactly to where you're focusing. So if you're focusing on something close, the horopter is going to be close. If you're focusing on something in the distance, the horopter is going to be out there in the distance. So yeah, this imaginary line can move depending on your depth of focus. So if it's farther away and you're comparing the angular disparity for something that's close, say the yellow point here, so in the same direction that you're focusing, but it's closer, there's going to be a bigger difference, right? So it's going to fall at 30 degrees away from your fovea in the right eye, minus negative 30 degrees in the left eye, and so the difference is 60. For the thing that's off to the left, the orange point, it's going to be at 60 degrees in the right eye and 30 degrees in the left eye for a difference of 30. So the bigger the difference, the closer it is. Or the closer it is, the bigger the difference. It's the exact same. So what does that mean about things that are farther away than the horopter? Right, there'll be negative numbers. So light from all points closer than the horopter fall in non-corresponding. So things that are farther away are going to have, I didn't change the text on this apparently, that are going to have uncrossed disparity. So they're going to be less than 0. Sorry, I've got my greater than less than sign backwards here. So this should be less than 0 here. So it's going to be at 45 degrees in the right eye minus 30 degrees, or a difference of 15. Or in other words, you get crossed and uncrossed angular disparity. So crossed just means that you've got, basically that you've got to cross your eyes. You've got to move your eyes to focus on these nearer points, so they're going to be farther apart in their angular disparity. Uncrossed means that they're going to be closer together in their angular disparity. So, big deal. You've got different images falling on your two different eyes. What information does that convey? Justin?
Does that explain why you get like two images for things that are closer? So like if I'm focusing on the board, I have like two fingers in my vision. Is that because the angles don't match up?
Yes, exactly. Yeah, because essentially they're not matching up. So things on the horopter are all going to match up. So if you're focusing on here, all of this is going to match up, but things that are closer are going to give you two different images for that. So one image falling on your left eye, one image falling on your right eye.
So why doesn't it happen with things past the horopter if it's kind of going the other direction?
It essentially does. So if you focus on your finger, so there should be two images of the board now. Yeah. Yeah, it does. It just goes the opposite direction. So the things that are closer are going to move out in their representations. Things that are farther away are going to move in. So the two images are going to be slightly different from one another. So this gives us what's called stereopsis. So you've got two different images, and you can take advantage of these two different images. And your brain actually does. There are cells in the visual stream that pay attention to differences in angular disparity, basically. So for points in the visual space close to the depth of fixation, images from the eyes are fused, resulting in stereopsis. So you're able to take these two images and put them together, and there's no difference. Stereopsis provides pretty fine depth information, and stereo depth information is based on the degree of angular disparity between the difference in the two eyes. So if you have two different images like this, and you present them to the left eye and the right eye respectively, then you should be able to come up with a perception of depth. And this is basically the whole concept behind 3D. So if you have the 3D glasses, you filter one polarity of light, you filter a different polarity of light, and you're able to present two different images to your two different eyes, and you're able to ruin Star Wars in yet another way. Anybody interested in seeing Star Wars in 3D? Kicking you out of my class right now.
They're just doing the new ones, though, right?
I sure hope so. I hope he stops
doesn't
at
matter.
the 3 that he's already ruined.
Does he not have enough money? What is it?
He's out of ideas.
I don't know. He did Red Tails, which I think is kind of the critics haven't liked. It's getting low reviews on the Tomato Meter. So yeah, I don't know. Although I don't know. I think you're right. I think he's just bored. Yeah. I think he does have enough money and he's bored. All right. So anyway, yeah, that's the idea behind 3D, is that you can present two different information to two different eyes. So these are binocular cues. So they require two different eyes. Another use for this is random dot stereograms. Random dot stereograms have sort of an interesting history. So the idea is that if you take advantage of this ability to present two different images to the two different eyes, our brains are really acutely tuned to this. So if you just have one image, say an aerial photograph taken from above, you don't get a lot of depth information there, right? So all you've got is sort of the two-dimensional image. But if you have two images taken from two slightly different vantage points and of the same point on the ground, if there's any difference between those two, your brain picks up on those pretty quickly. So people in World War II who were trying to camouflage tanks, for example, what's a good way to camouflage tanks from aerial reconnaissance, from airplanes flying over?
Cover them in leaves.
Cover them in leaves, or cover them in a big tarp that looks like leaves, right? So it's a big square sort of tarp, but it looks like leaves. It looks like the ground underneath. So if you're just taking a picture from above, what does it look like? Nothing, the ground, right, exactly. But if you take two pictures from above, focused on the same point, and you present those two pictures to two different eyes, what's going to pop out? The square, right. You're going to be able to see that, oh, this square is much higher. It looks like the ground, but it's a square-shaped section of ground that's approximately, 2 or 3 meters high. And so that's really going to pop out. So this is where this idea of random dot stereograms really comes from, is work in World War II of trying to counteract camouflage, basically, to get around this camouflage idea. And so what you can do is take two images. These two images, these two sort of random static images, are exactly the same, except for one little section in the middle, where we've taken the black and white squares, black and white pixels, and shifted them over. So this is another way of looking at it. So ones are white, zeros are black, and here we've taken A's and B's instead of ones and zeros, and you can see that in the image on the right, we've shifted it over slightly, and then just filled in ones and zeros randomly on the row that we've shifted it over. So if you present these two images to the two eyes, and you get them to fuse together, so you have the one image overlap on the other image, is there any angular disparity for most of the picture? No, there's not. So the two images should overlap exactly, except for in that little square that you've shifted over. There is going to be some angular disparity. And so what does your brain interpret that as? As depth, either coming out or moving away from you, depending on the direction that we've shifted it. So if we've shifted it out, then it's going to appear like it's coming towards you, because angular disparity moving in the outward direction is closer. If we've shifted it in, then you're going to interpret it as moving away from you. So if you do something like this, if you diverge your gaze, meaning if you either change your focus from where the actual depth is to something either behind or in front of this image, and you get the dots, these two dots, to line up on your two different eyes, so to line up on your two different retinas, then you should be able to see something in this image. Can anybody see it yet? I think I need to get closer. Oh, there it is. Do you want to move forward? Because I've got a bunch of these.
I used to have a book of these when I was younger.
Could you do them?
Yeah.
Okay.
But I think he's right. I think I'm just too far away. I
Yeah.
have to move the book in and out.
Right, okay. Well, feel free to move if you want to. We've got a bunch of these things, like I said. Well, yeah, why not? Anybody not able to do these? Like, in general, for the books, you're just completely unable to do these things? So, for those of you who can do them, what's your strategy?
I just unfocus my eyes.
What direction do you unfocus? Do you focus closer or farther away?
Closer.
Closer. Yeah, closer is always easier. Well, for me, closer is easier. And that's going to result in the illusion going the right direction. So if you focus farther away, the angular disparity is going to go the opposite direction, right? And so things are going to appear to recede away from you instead of popping out toward you.
I feel like I almost could do it and then refocus on it and it would still be there.
Mm-hmm.
Like trick myself that I was looking at it normally in the center, so I don't know what was going on. So I would make my eyes freak out and then it would go back to normal.
Yeah, so when you're unfocusing, so what's the deal with these things? Maybe to take a step back. I mean, what do you notice about them, say, as you move from one side to the other? They sort of repeat, right? They've got a pattern to them. So this actually has a long history. This whole sort of unfocusing your eyes on these things has a long history. So if you've got something like a tile floor or a tile wall where the pattern repeats over and over again, you can unfocus your eyes and trick your eyes into lining up two different things that don't really line up, right? So remember the correspondence problem that we talked about earlier? So essentially, what is the correspondence problem? Give me some blank books for that.
One of the essay questions for the test.
Is it actually one of the essay questions?
So it's all the little. I guess we should know that.
All right, so let's talk about the correspondence problem for a second.
Say question 2. Let's write this down.
No, we didn't talk about this today. We talked about this a while ago. Is this helpful? So this is the image that's falling on the left retina. Well, actually, it's upside down and backwards. But this is what you can see out of your left eye. Where does the boat have to be on the right eye? It's got to be on this same plane, right? If it's down here, then it's probably not the right boat. If it's up here, it's probably not the right boat, right? So the correspondence problem is, how do you pick the image in the right eye that lines up, that corresponds with the image in the left eye? So what random dot stereograms do is they take advantage of this correspondence problem because they've got multiple things in the right eye that could line up with what's going on in the left eye. So you've got this pattern here that could line up with this pattern here. So if you just change your focus, then the two images you can get to line up with one another. It's just a matter of finding what depth do you have to focus on in order to get those two images to line up, in order to have that angular disparity for everything else come out to be 0, except for the thing in the middle where there is still a little bit of angular disparity. So the background, there's no angular disparity, but for the thing in the middle that's been shifted a little bit between the two eyes, there is a bit of angular disparity, so you can perceive that coming out. So what's the correspondence problem?
Figure out how we know which image is the same image in both eyes.
Right, exactly. So usually we solve it by things like, well, it has to be on the same horizontal plane in the two different eyes, and these are actually a little bit angled. They're up and down. But what you do if you're making one of these things is you take advantage of this correspondence problem. Or you can trick your eyes into seeing things, seeing depth that isn't actually there. Say if you're looking at a tile floor, where you get one tile to correspond to the other tile by changing your depth of focus, by focusing farther away. I feel like I'm sort of mangling this explanation. Does this make sense? And I'm just over-explaining? Also possibly the case. All right, so nobody's going to get these because they're too far away. Is that the idea? All right. Well, that's disappointing because I've got so many. How about this one? Does anyone get this one? It's like you can almost get it. You can almost convince yourself that there's something there. It's not surprising that you can't get anything in this one because there is actually nothing in this one. Haha. So if you do show random patterns to people, some proportion of people will actually report seeing something there. Particularly if they believe in ESP or the patterns are presented in the left visual field. So if you can convince yourself of things that don't actually exist, like ESP, then you can convince yourself that there's something here. There was a recent study that just came out like a couple of weeks ago, though, where they presented people with random patterns like this and said, in some of these, did I talk about this in here? About the face thing? In some of these patterns, there's a face. In others, there's not. What we'd like you to do, and the face is just sort of distorted, what we'd like you to do is tell us when you see a face and when you don't. And so people about 40% of the time actually said, yeah, I can kind of see a face in there. And so for these randomly generated sort of random dot things, they were coming up with faces where there wasn't actually a face there. So what the researchers did, though, is they saved all of those images. So they took the average of all of the ones where they said there was a face, and the average minus the average of all the ones where they didn't say there was a face, and guess what comes out? A face. So the average of all the ones endorsed as a face actually comes out to a face. So what they're seeing is if there is just randomly sort of a face in there, they pick up on that pattern, and they do it consistently. I'll show you the data next time. It's actually pretty amazing. Okay, so I've got way too many of these things apparently. All right, so back to the correspondence problem. So the correspondence problem is how does the visual system pick out the corresponding images on the two different retinas? So you've got this angular disparity. How do you know that it's not the same thing just at a different plane, or is it or is it two different things at the horopter? Right. So matches may be made by specific features of the objects. This may not work for objects like random dot stereograms where there really aren't any features or where the features repeat over and over and over again. And we really don't know exactly how the brain solves the correspondence problem. We know that it does. It's probably using a heuristic or a shortcut, but we're not entirely certain how this is actually happening. Okay, so just really quickly, let's talk about what's going on in the brain. There are cells as early as V1 that are paying attention to retinal disparity. So you do have cells that fire when you've got different images in the two different retinas. Most depth processing takes place in later stages, though, so V3 and on. And you've got parietal neurons that process higher order depth information incorporating binocular and pictorial cues. So you've got places in the parietal lobe that are paying attention to depth in space. And we'll pick up next time with what are these pictorial cues that you're actually paying attention to. All right, that's it for today.